That's not very good. And you know, it's not the homework grade per se that matters, but I would worry, right? You need to be putting in more effort because you're just going to struggle on the exams. If you know, high 40s, I don't know, maybe not so bad. But, you know, just don't get fooled into thinking, you know, I blew off the homework and it worked out all right. You know, you'll get hammered on the exams if you're not really up on top of the work. So the exam is Friday. We'll be having some sort of reviews later in the week. More detail probably by email, but certainly Thursday night, possibly Wednesday night. Some combination of myself and Pete Kiernan, okay? Plus which, you know, on Thursday, and of course there'll be the two recitations, and you know, I'll be available. Quick word on the exam, it's only on special relativity. You're pretty much everything in special relativity is fair game, you know, up through the momentum problems and some of the stuff we're discussing now, even though I'm not really going to assign homework on it. We didn't cover the Doppler shift, and so you're not responsible for that, okay? I'm going to talk about general relativity today. You're not responsible for that. And then on Wednesday, we'll move on to the beginning of quantum mechanics, even though we have the exam on special relativity on Friday. So any questions? Procedurally? Business questions? Other questions? Yeah. Excuse me? I don't think I'm going to post practice problems. However, look, the book has a lot of problems, right? So, you know, work the book's problems. Yeah?
You mentioned early on in the class that we get a formula sheet.
Okay, yeah, so I will put a formula sheet on the exam.
Will it be posted online before the exam?
No. I mean, look, what is it that you would want to know on this exam? I don't want you to memorize things, right? That's not the way you're supposed to learn physics. And the reason I would post a formula sheet was so you, for instance, wouldn't have to remember where the minus signs go in the Lorentz transformations, right?
I was wondering if it would be posted online so that we could kind of look over it and kind of get a feel for what we actually have to memorize, learn out of the textbook versus.
I understand what you're asking, and I'm not unsympathetic, but the main point is, think of the hard problems in this first homework set. I give you one cold, can you work it? Right? That's what you got to be thinking about. You know, I've got Anna doing some wild thing and Bob doing some wild thing, and there's, you know, some rocket ship or whatever, and I ask you about clocks. You've got to be able to deal with as complex a problem as is in this homework. All right? But I'll give you all the formulas you need. There aren't that many. There's the Lorentz transformations. There's the velocity transformations, right? And there's a little bit more on momentum and energy. That's all there is. And frankly, you should know, I mean, I think I'd be fully justified not giving you any equations, right? Because it's not really that much to memorize, except perhaps where the minus signs go on the Lorentz transformations. But I didn't. I'm going to give you the formulas. I might post them, but that's just really not the right way to study. I mean, the point is you shouldn't be looking at the book and thinking, do I have to memorize this, don't I? Right? I mean, the stuff that you might have to memorize, the equations you'll have. But I'm going to make sure that, I'm certainly going to try to make it such that if all you're doing is memorizing equations, that's not going to be enough. Right? You got to understand it. And so certainly you guys have to get this, the second part of the chapter with momentum and energy, algebraically can be a bit harder, but it's straightforward. You know, it's a little bit harder to get completely tripped up just in terms of what are we doing, right? You got to get your mind wrapped around how to apply the Lorentz transformations to these, you know, problems of length and time. You know, the first homework set, okay? So make sure that's under your belt. Fair enough? Yep.
Will we have the second homework back in time for the test?
I don't want to, I can't promise it, but I will post the solutions today, tomorrow. Okay. So I have just a little bit left up on to discuss on special relativity. Didn't mean to do that. I've made things worse. There was a lot. That's what I was looking for. Oh, wait a minute. Okay. So now those lights will come on in minutes. I'm sorry. No, I turned them off, didn't I? The switch set on. Okay, that's a little better.
One of them, they go opposite.
Uh,
It says on and off, and one of them goes up and one of them goes down, even though it doesn't look like that.
Well, this is how we'll do the class for now. I guess I'll stick to this board. If you could, yeah, print them both, that'd be great. Appreciate it. All right. So I talked about the fact that space and time can be best thought of actually as being an equal footing x and ct in this space-time 4 vector. And there's something very similar going on with momentum. So this is just as a reminder, what would p x prime be? All right, so in say the moving frame, Anna's frame, it would be gamma u prime m ux prime. Okay? And there was that awful formula for gamma u prime in terms of gamma, in terms of other things. It was gamma v times gamma u times 1 minus ux v over c squared. That's that hairy bit of algebra that I showed you. Okay, that's times m. That was gamma u prime. And ux prime, this you should know. It's ux minus v, the classic Galilean thing, but divided by this same ugly term. So remarkably, those cancel. And I end up with 2 terms, one from this and one from that. Gamma v times gamma u m ux minus gamma, sorry, I'm right this way, minus v gamma u m. This really is annoying that it's so dark. Okay. And then I'll note that is just p sub x. Okay? And we did this before. This is, I can divide it by, if I write this times c squared and divide it by, well, c and c again, v over c is beta, and this is the total energy. So all of this is beta energy over c. So px prime equals gamma v px minus beta e over c. And that is very much like the x Lorentz transformation equation. Okay? Py prime, it's gamma u prime m uy prime. Okay. Gamma u prime is ugly. It's gamma v, gamma u, 1 minus ux v over c squared. Uy prime, or there's an m. Uy prime, remember, it was kind of simple in the numerator. Uy prime, the velocity wasn't changing, but there was the denominator still had the time piece. And in particular, it also had a gamma v term absent in the x expression. And so this ugliness cancels. But then gamma v cancels gamma v. And so in fact, this is just gamma u m uy. That's actually a nice result that I'm not sure we said yet. Remember we did the velocity transformations. Not surprisingly, ux is different from ux prime. And now even though x and y, even though y and z are the same as y prime and z prime, their velocities weren't because of this denominator. But the momentum, the ugly terms completely cancel. And so this is actually a very nice result, that the momentum in z and y is the same. Okay? And then so finally, well, so that's momentum. And then there's one last thing that's worth exploring, which is energy. Energy prime is gamma u prime mc squared, which is gamma v, gamma u, this same formula, 1 minus ux v over c squared times mc squared. Okay, and I'm going to rewrite this. I'm going to swap the order here. It's gamma v outside, and then it's gamma u, all of this, which is v over c times gamma u uxm. Oh, and this, sorry, the c squareds cancel. So what is it? It's v times gamma u m ux, the minus sign. Excuse me. And then there's that term, which is plus gamma u mc squared. Okay? And this, of course, is just px. All right? And so, finally, if I divide this side, just a simple normalization, divide by c, then this term becomes minus v over c minus beta px. And this is e, and I divide it by c. A lot of algebra. You're not, I mean, you don't, this is a little bit of formalism that, you know, I'm not going to stress. I just wanted to work it out so it wasn't magic. And I have 4 formulas. We're really not going to get these lights back? They'll come up. Yeah. Okay, good. Those 4 equations, this is exactly the same form as we had for x and t. And that's the neat thing. That's why I did all of this. So what we say is that there's a 4-vector for momentum, which is the spatial momentum, the same way as before, and energy over c. Okay? And then the Lorentz transformations. How Anna sees the momentum and energy compared to how Bob sees it is given by the formula P prime is A times P, right? Where A was, well, it was just, you know, this matrix was just, okay, Y and Z go along for the ride. The X part has some part of px and some part of e, and this gamma term. And so this was minus gamma beta, 0, 0, no, sorry, it's gamma. Sorry, it's 0, gamma, 0, 0, minus gamma beta there. It's 1 along the diagonal. It's gamma there. It's 0, 0, 0. It's 0, 0, 0, 0, 0, and minus gamma beta. We don't need to write this down again. We wrote this last time, right? Just wanted to show there's this kind of beautiful symmetry. So time and space now sort of become on an equal footing, and they're mixed together by moving from one frame to another. So are momentum and energy. And it's not actually surprising in a way that momentum and energy should get mixed up. I mean, just at a very basic level, and this is just a classical result, you know, if I have a thing and it's just sitting there, and I'm in a frame and we're all just sitting there, I would say it doesn't have any momentum. But if I'm in some other frame, you know, now the thing moving past it, I see it moving as I walk past it. It has momentum in this other frame I'm in. So the fact that energy momentum gets mixed up, maybe not so surprising, and it certainly does in relativity. So then the one just final comment about relativity is we said with the x, the position time 4 vector, that there was this remarkable thing, that there was this new definition of the length of a vector, which is I take the length of the space part and I subtract I square the square of the time part, and that thing is a constant. It's an invariant. It's not just a constant. That's a little different statement. It's an invariant. Both frames see it the same. In this case, it's very simple too. This is also conserved, or invariant. Similarly, if I have a momentum, if I look at a change, the difference between two states where it's a delta p squared, that same delta p squared will get observed the same from both frames. But what is this? Again, simply, this is, even though this is typically called the time part. So anyway, the momentum piece and the place that was the second part, which for space was the time part. Here it's E over C, so it's this thing squared minus that squared. So it's simply p squared, normal old p, well, normal old gamma times mv, minus E squared over C squared. And if you remember, in your homework, you derived this. So divide this by c squared, and you see that p squared minus E squared over C squared is m squared C squared. Okay? The rest mass squared times C squared. And so the length of the 4 vector is m squared C squared. And I said it was an invariant. And that makes sense. It's the rest mass of the particles, okay? And that is going to be, I mean, we all, even though people see different things, we all know what the mass of the muon is. Even though the muon's moving and I see it moving, I know what its mass is. I know what it would be at rest. Everyone agrees on what this is, and it's an invariant for all frames, okay? So it all nicely ties together. Okay. So that's all I'm going to say about special relativity, unless there's any other questions before we leave it aside. Okay. So now the book briefly talks about general relativity, and I want to talk about it. General relativity, there aren't really easy problems. And so I'm just not going to, this is not a sign. You're not going to be responsible for it on an exam. But having done special relativity, it certainly makes sense to talk about it. So let me talk about it briefly. So special relativity, Einstein developed leading up to this amazing year when he published 4 different results in the same year when he was still quite young, 1905, I believe. Let me check my notes on that. Yeah, 1905. In fact, that's, to be academic and sort of a little bit pompous, it's called the miracle year, but in Latin, I think Anna Mirabilis. Okay, because of, I mean, he did publish 4 phenomenal papers, and I'll talk about a couple of them later. And then he sort of, he did work on other things, but then he spent quite a while grappling with the concepts which came out to be general relativity, okay? And mathematically, general relativity is a lot more sophisticated than special relativity. I've actually given you, especially when I did the 4 momentum version of things and the Lorentz transformation version of things, that's really, there isn't much more to special relativity. I mean, you've seen it. Again, you work it into electricity and magnetism, it gets a bit more complicated, but you've seen a good taste of it. General relativity, the mathematics is very hard. But the concepts, I mean, there's a very interesting analogy. It was developed in a similar way, basically through sort of one fact that people sort of measured, if you will, and then sort of Einstein was the one guy who took seriously that there ought to be an underlying concept behind that fact. And once again, sort of all on his own, no one was really asking him to think about it, developed it and dreamed it up. And also, like special relativity, it changes everything enormously. Special relativity, time and space are mixed, etc., except that you can't see it until things are going close to the speed of light. Okay? General relativity, similarly, it replaces Newtonian gravity, just that the force of gravity is g m1 m2 over r squared. But it's, the effects of it are subtle unless gravitational fields are intense. Okay, like say near a black hole. And so he just dreamed this up because he wanted the laws of nature to be sort of understandable and symmetric and sort of logically consistent. But it was really kind of a leap of faith to do what he did. Okay. So what did he do? Well, the one thing that he took seriously and thought about that other people hadn't thought about was the equivalence of inertial and gravitational mass. What do we mean by that? We have F equals ma, right? And m there, as you know, is, there's one way of looking at it where this is the definition of mass. Mass is the relationship between the force you stick on something and then how much it moves in response. And if mass is big, for a given force, acceleration is small. So that's clearly the inertial mass. Now, what if the force we had was gravity? Okay, in some situation. I have a mass, me, I'm stuck to the Earth. Earth has capital M mass, that's the force. And ordinarily you just cancel little m. But in some sense, well, why in the world should that be? The way we think of forces in modern days, electrical force, we say, it's because something has an electrical charge. What's an electrical charge? I don't know. It's something that allows it to have electrical force. So we'll just use the term charge when there's some force. And we say, the thing is charged if it feels the force. So in some sense, I should really say that we have a gravitational charge, m. I'm just sort of redefining things. Why should this gravitational charge have anything to do with inertia? Right? I remember when I was your age and someone first said that, I said, of course, it's still the mass. They should cancel. But no, that is not thinking deeply. Why should they be the same? So why could, and let's say this is one particle, and it has one acceleration, and this would be the inertial mass. Let me write it as I1, and this would be the gravitational mass, G1. Okay? So if we have a second particle, this would be the force on one particle. If we have a second particle, we'd have m2, m inertial 2 times a2. And if it's also sitting here getting affected by gravity at the same location, r squared, I would write that. And if I just divide the two equations, then a1 over a2, I would have m1, mi1 over mi2. I'll put those on the other side. So I have mg1 divided by mg2, divided by mg2. And I have m inertial 1 and m inertial 2 there. Sorry, that's inertial 2. All right? The ratio of accelerations should be this combination of the inertial and gravitational masses. However, Galileo made his name first, right, by pointing out there was Aristotle had written down one time, of course heavier things fall more quickly. And for 1,000 years, we're in the Dark Ages, and no one questioned Aristotle. He kind of was, I think it was just sort of an offhand thing. He said a lot. He wrote a huge number of books. So Anyway, it was clearly wrong. Well, it wasn't clear. It was wrong. And the reason, of course, it wasn't clear is because for most things you might drop, well, it's hard to tell time differences anyway. And unless something's really light, and then air resistance affects it. And so Galileo actually did careful measurements. And he actually literally did do some demonstrations from the Leaning Tower of Pisa. And he dropped 2 balls, okay? And he showed that they hit the ground at the same time. Which is to say the acceleration in a gravitational field for the 2 particles is exactly the same. And that's only going to be the case in general if the ratio of gravitational inertial mass is the same for all particles. And it's not a question of, oh, I'm going to redefine how much, the ratio of the gravitational to the inertial mass. That's really, if you just think about it a second, that's just redefining g. Given the value of g, these basically have the same value. The more point is that it's always the same for all particles. So how you have inertia and how you feel gravity is the same for all particles. Galileo proved it. And it took till Einstein to say, that's weird. Well, I'm sure people had said that was weird, but Einstein really took seriously that that was weird. He said that is really deep and that is really profound. And he formulated this as the principle of equivalence. And further, if that's sort of the mathematical, experimental fact, if you will, sort of like Michelson-Morley, although much, much more direct and much, much more well-known and had been known for 400 years nearly, okay? 350 years. Einstein said another thing. He said, well, boy, if those are really the same, then these situations should be the same. This is all under the heading of equivalence principle. The equivalence of inertial and gravitational mass, or here, the equivalence of inertia and gravity sort of as a frame. What do I mean by that? If I have, I guess this is going to be Carl in a rocket ship that's accelerating, and I just happen to pick his acceleration equal to 9.8 meters per second squared. And so the rocket ship's accelerating up and Carl's kind of glued to the floor because it's accelerating. That is not just happens mathematically to be the same acceleration as Carl sitting on the Earth, but is in fact the same situation as Carl sitting on the Earth affected by a gravitational field. Okay? These are the same. Not just happen to have the same effect on Carl, but are the same. Are the same. Okay? Similarly, if Carl's out there in the cosmos and his rocket ship is now no flames coming out the back and he's floating along, Carl's having fun, floating upside down, okay? That is the same as if Carl has got himself into an unfortunate position here on Earth and is accelerating downwards and is about to hit the floor but hasn't hit it yet, all right? If you do the Cedar Point up here, what it's called, where you drop, right, you feel weightless, okay? Those are the same. How can they be the same? What Einstein did is he reformulated, he constructed a mathematical system where space and time are affected by the presence of objects and warp, okay? And the presence of gravity is that it actually just changes the way you move through space-time. And so this is literally the same. Accelerating due to some other force, if that acceleration is fundamentally the same as the way the presence of the Earth accelerates me through space-time. And it's hard to make that more sensible. I can draw, the book has nice pictures where we think, where you sort of see a grid, and then it's sort of distorted a little, like that. It's distorted like this by a mass. You've seen the pictures in the book, I'm sure, right? So the gravity is warping. This is a XY grid. Of course, we really live in three-dimensional space, so it's impossible to draw in a simple three-dimensional way. But a straight line, which is what you feel when you're not near a gravitational object, changes when you're near a gravitational object, okay? And I know that's very abstract. And what do I mean by that? I mean, I can't really say much more. I can try to do a little better. Last time, we talked about the light cone for a person, okay? And I said, I'll draw my light cone right now. Not my light cone, but my movement in space-time from a special relativistic point of view. I'm sitting here at one moment in time, and I don't translate, and a little while later I'm there, and a little while later I'm there, okay? That was my movement through space-time. You know, I mean, I just added a CT axis and said something profound about the fact that I'm just standing still, right? But okay, no, it is a little more than that. I mean, the fact is space and time are mixed, and if you went racing past me relativistically, you would have seen my movement differently in this, okay? Similarly, you could find a path that has the minimum surface distance in this warped space-time, and if I'm out in free space, away from any gravitational object, and I just sit there, I move like that in space-time. But if you put a big object there in space, the shortest path is kind of this warped direction, okay? And in the case of us sitting here right now, it's a warp, it's kind of like a line that just hits the surface of the Earth, and we're just kind of stuck to it because the space-time is warped such that, you know, the way we would like to flow without doing anything in space-time is just to be stuck on the Earth, okay? And acceleration is a movement off of that. The normal force from the Earth, from the seat, the floor, it provides that normal force, and then we feel that as an acceleration, or a force due to gravity, you know, normal force, because we're not just flowing along the space-time free path, which would be to be plummeting towards the center of the Earth. Okay? So that's as good as I'm going to try to describe it. You can read the book and try to get another description, okay? But that's the reality. And it does, though, you know, this four-vector and four momentum and all that, right? The mathematics is somewhat similar. You write down that you no longer have simple space. You have space with CT mixed in. But now instead of just that's that, I have equations which relate energy and force to a combination of X and CT. And then it warps everything. And you basically solve kind of like potential problems. You find the potential, but it's not the gravitational potential. It's the metric of curved space-time. Okay. So anyone have a question at that point? That's as good as I can do. All right. Okay, but having said that, now there are a number of results from all this. Okay. Let me just say them. I mean, first thing is, you know, there's the whole philosophical thing that you generate a mathematical framework where literally these are the same now mathematically, which is amazing, right? Here, clearly these are physically not the same, you would think. But in the theory of general relativity, they would mathematically be described the same way, okay? This force from the Earth standing still on it, the normal force, versus the normal force when you're accelerating. They mathematically will be the same description. Now, if that's all it were, it would be kind of an interesting exercise. But, you know, okay, you know, so what? But the fact is that, okay, so if you apply general relativity, this very complicated mathematical machinery, okay, to us sitting here in this room, it turns out that these very complex equations simplify down to Newtonian gravity. However, it's different Newtonian gravity when gravity is strong, or even when gravity is not real strong. Like the Earth in this respect is not strong gravity, okay? Even the sun, not strong gravity. However, subtle, small effects are measurable even at the scale of the gravity of the Earth, okay? and certainly at the level of the gravity of the sun. Okay? So in fact, there are a number of gravitational effects which can't be explained with normal Newtonian gravity. They need general relativity. In fact, that's the way we've best tested that general relativity is correct. Another prediction is that there's gravitational waves. Okay? I'll come back and mention that a bit later. The whole notion of cosmology, the overall expansion of the universe since the time of the Big Bang, there's no real way, well, actually there is a Newtonian gravity version of the equations of the Big Bang, and they actually get the basic features, but they don't come close to describing all of the features of the Big Bang. And that has to be understood using general relativity, because essentially the gravity was very intense at early times during the Big Bang. There's another thing, which is light is bent by gravity. And there would be no way of knowing that in normal, if you just had special relativity. I mean, we kind of said in special relativity, we got this hint that energy equals PC should be the description of light. But like, it doesn't have mass. So how would, especially if you go back to like, Maxwell, light is an electric and magnetic field. Why should that be bent by gravity? But in fact, light is bent by gravity, and that's been absolutely very well confirmed. In fact, that was the first confirmation of general relativity. Gravity affects time. Okay, and I'm going to mention that in a second. And also, there's effects, especially like Mercury, which is so close into the sun. There's a part of its orbit is affected by general relativity. Okay, so the book goes through one example. I'm just going to write it down. I'm not going to work out it's a very small amount of math they work out, but it involves the Doppler shift. But we can get without even writing the math down, we get the idea here. And this is the effect that gravity has on time. Imagine two people in a spaceship. Let's put Bob down here and Anna up here. And Bob has a flashlight, which goes off, and the light moves up, and then Anna sees it. Okay? And the spaceship is, well, I won't draw it. The spaceship is accelerating. Now, I didn't talk about it at all, but there's a Doppler shift in relativity for light. Right? It's not surprising at all, but you have to understand it using a relativistic expression, and it's not quite the same as the Doppler shift you probably have learned for sound. Very similar equation, but not quite the same. So what that means is, well, if they were just moving, that wouldn't do anything. Well, first off, the light is seen as going at a velocity c. That was the whole we've been talking about for 3 weeks. But I'm not talking about that. I'm talking about the frequency. But the frequency gets changed if they have a different relative velocity to each other, right? That's a Doppler shift. But since they're accelerating, in the short time between when Bob emits the light and when Anna sees the light, it's accelerated. And so she sees the light at a slightly different velocity. She's basically got some extra oomph by the time she sees the light. And so she sees the light as somewhat redshifted. Okay? No big deal. I mean, they're there on the rocket ship. They say, so what? So the light got redshifted. But again, Einstein says, no, you know what? That's exactly equivalent to where if Bob is just sitting on the surface of the Earth, if this acceleration has happened to equal to g, and Anna is up on a cliff, or up on a ladder, maybe just one floor up in the building, and they do the same experiment. It's the same. Okay? So, Anna will see a frequency which is less than, instead of Anna, this is top, than Bob. This is below. And how are we going to interpret that? Suppose they use some natural line in an atom. That's our frequency standard, the atomic clock. It's based on vibration in an atom, electronic vibration in an atom. So it's a frequency standard. Basically, time, there's an amount of time between beats in a wave, 1 over frequency, or the period, maybe I should have said. So if Anna's seeing a lower frequency than Bob, time for Bob, time below, is slower. But be careful, it happened to be below, but the below was that it was, if you think this through, the below is due to this acceleration, which is due to the gravity. The below is, Bob is in a higher gravitational field than Anna. That's the analogy here. Time is slowed down by gravitational fields. And, I don't know if you know this, but GPS technology, okay, you know how GPS works, just really roughly? It's just triangulates. You're sending signals to satellites, and it just measures the time difference sending, I mean, and it gets down to the foot scale, right? So if you have a GPS transponder and it's talking to a satellite, and you have a GPS transponder and it's talking to a satellite, the two signals know the different time it takes, and then they do just simple triangulation using trigonometry to figure out where you guys are, okay? Or actually, I guess the way it works is one of you and two satellites, but nonetheless, same idea. And you have to take, the GPS has to take into account general relativity. It wouldn't work if we didn't have general relativity, because time is slow enough between here, the surface of the Earth, and near orbit, which isn't very high up, like 100 miles up. The time difference up there compared to here, time runs slower up there, okay? So in fact, when you get on a plane and you fly across the country, if you fly a lot, you're going to live a little longer. You get this big dose of gamma rays, cosmic rays, maybe you get cancer earlier, but you'll live a little longer because, well, there's a special relativistic effect because you're going fast, but there's actually a much bigger general relativistic effect because you're up in a weaker gravitational field. Okay? If you live in Denver, you're going to live longer. Yeah? Yes. Oh, I'm sorry, you're going to live a little shorter. Sorry, you're going to live shorter. So when you get in a plane, the special relativistic effect, though, I think is weaker than the general relativistic effect. I said it backwards. Yeah. All right. 5 more minutes. So some more fun things. Einstein came out with this in 1915. And I said that mass interacts with light. It's something there wasn't a prescription for until we had general relativity. People didn't, if he hadn't come out with special relativity, when he came out with general relativity, they would have, he would have been ignored. But he came out with general relativity and people were at a loss. It was this incredibly more complex and dense framework. By that point, special relativity was accepted. So they took it seriously, but they sure wanted experimental proof. And the best proof people could come up with was the idea that if here's the sun, and here's some distant star, and here's the Earth. Of course, I'm exaggerating the distance here. This is way off the distance, but just in terms of directions, this drawing is how I want it. Some light from the star that was headed this way will bend and intersect the Earth. Yet if you look backwards from the Earth, you appear to see the star at that location. And people thought this through and they realized if this was going to work, we're talking grazing incident, a star that's just below, the visible edge of the sun, and then, you can't see that because the sun's real bright. And then in 1919, there was a solar eclipse, the first solar eclipse between when he published his paper and then, but it was in the southern hemisphere, so a big expedition went out, and they sailed down to the South Pacific somewhere and observed it, and it just dead on matched. Essentially, there was a star, they knew where it was, and as the Earth processed in the days, the thing that lined up, and they saw the star's position. Well, they knew it was there, and they saw the position appear to be there due to the bending from the Earth. And in fact, now in modern cosmology, it is becoming a benchmark tool in cosmology is to study the effects of mass by looking at the distortion it does, bending of light, the so-called lensing of light of background objects. That's one of the ways we know about dark matter. Interesting human story, tied up in all this story about general relativity is black holes, neutron stars. There was a young guy by the name of Chandrasekhar who postulated the existence of neutron stars. His advisors, whose name was Eddington, who's the guy who mounted this expedition and got famous. Well, he was a great physicist. He did a lot of great things. He trashed Chandrasekhar in public at a meeting, and their relationship didn't recover for, I don't know, 50 years or something like that. I don't, full story. It was bad. It was like one of these nasty famous disputes in physics. Said that Chandrasekhar was wrong about neutron stars. But of course Chandrasekhar was proven right. And is one of the giants of 20th century physics, more so than Eddington. Anyway, so that was the first direct measurement. I'll say just a couple more words because this is fun stuff. This proved there was general relativity. General relativity has been really exquisitely tested, and the way it's been tested is when you have a supernova, as you probably know, the inside of the star collapses, and you can have a black hole, you can have a neutron star, white dwarf. There are many. It turns out most stars come in pairs, binaries. I think something like roughly, not an astronomer, roughly like half. Pretty amazing, you know, you think of all solar systems as being like ours. First off, something like half, maybe it's a third, maybe it's more, but something like half of all stars, two stars together. And then if one of them goes supernova, now you're going to have a star and a black hole, or a star and a neutron star. In some cases, you have a black hole and a neutron star next to each other. And neutron stars are spinning really fast, and they emit jets of radio waves. And they're spinning at around 10 hertz, 10 times a second. So imagine that. They're typically a mass similar to our sun. They've been compressed down to this object, which is, I think, tens of miles across, and it spins at 10 times a second. Just try to wrap your head around that. And so you see those, and it's a thing. If you get if the pulsing, the radio signal comes out of the poles, if things work out right, it points at the Earth. And these were first detected on good radio receivers and big telescopes. These things that go boop, 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 boop. Just turn on an AM signal and you just hear it, okay? And people have watched a binary pulsar pair, so it was a neutron star around a black hole, they think, over a course of a decade. And they've seen, you can tell a lot by observing these beats of a neutron star. And they're able to tell the orbit, basically, and they see the orbit decline and they see the neutron star slow down. And all of that is described in gravitational, by general relativity. Basically, the whole system is emitting gravity waves and losing energy. And the two are spiraling into each other. And there's a Nobel Prize for that because it's an exquisite test of general relativity. And the other thing that's going to happen in the next 10 years or so is we're going to have a class of gravity waves detectors turn on. There's one called LIGO, which has been going for about a decade, but has not been sensitive enough now, but soon will be, that it should be able to see the infall of two black holes, or a black hole and a neutron star. And there's this amazing set of gravitational waves that come out over a period of a day or so as the things collide with each other. And upgrades to the LIGO in the next decade or so, they should start to see, people don't know how many times this happens in the nearby universe, but based on estimates, you have some idea, and you're going to start to see, you should be reading in the news, hopefully in the next decade, about a whole bunch of measurements of the gravitational waves. And that's all from general relativity. And I'm sorry I kept you late, I'll stop there. If there's any homework left, could you bring it back?